recording.
Okay.
And you start the seminar, right?
Good day to everyone. It's my pleasure to introduce Maxim Grigoriev, who from the University of Mons, and actually from many other places, but first now at the University of Mons. And he will talk about graded geometry of local gauge theory. So please, Maxim.
Okay, thank you, Alexei. Thank you, Juan. Many thanks for invitation to give a talk here. It's a honor for me. So I'll talk about certain graded geometrical structures which show up in studying local gauge theories, and it's a some kind of long-term project. So I'll talk about present-day understanding and recent advances. So let me say a few words about the relation between graded geometry and gauge theories. So there are many approaches, one way or another, to gauge theories, where you can see some graded geometrical structures appearing. Let me mention some of them. They're actually in the list. So first of all, and this is probably the most basic in a way, is the Batalin-Vilkovisky formalism, and it's the most important one for me. Then there is a version of the very interesting construction, which is nowadays called known under the name of AKSZ because of the first letters of the names of the authors. It's a construction which allows to construct BV formulation of a topological model in a very elegant way, and the input data is a certain graded geometrical object, so-called symplectic Q-manifolds. Then there is another approach which can be considered as a variation of Batalin-Vilkovisky formalism or extension of Batalin-Vilkovisky formalism in such a way that it takes locality of the theory using manifestly into account using the geometry of jet bundles. And the powerful technique arising from this approach is that of local BRST cogomology, which found many applications in gauge theories. Then there is another approach which was developed in the context of higher spin theories, and this is called unfolded approach, where the equations of motion of a gauge theory take the form of free differential algebra, which in turn is also related to certain graded geometrical structures. Closely related is the free differential algebra approach to supergravity. And let me finally mention another two sources of ideas which are important. The first one is so-called BRST first quantized, or nowadays it's more BRST first quantized approach, which was developed in the context of string field theory. Nowadays, people typically talk about L infinity. It's like a modern name for this and more precise, perhaps. And finally, you can also find many parallels with the structure arising in Fedosov quantization of symplectic manifolds. So, so you see that graded geometry enters the game immediately after you start to develop a geometrical approach to local gauge theories, but still, all these approaches have certain advantages and drawbacks, and also the relation between them is not always obvious. Also, I forgot to mention the important input from the geometry of partial differential equations. Okay, so let me start by recalling you what the AKSZ construction is, because in some way the geometry and the formalism I'm going to talk about can be considered as a far-going generalization far-reaching generalization of this construction. which is applicable beyond the context of topological theories. So what's the geometrical setup of this AKSZ? So there are two graded manifolds. Everything in this talk is going to be Z-graded. It goes without saying. So all manifolds are Z-graded. And systematically, I identify, so I assume that there are no super genuine super coordinates. So the super degree is just the degree modulo 2. So the two degrees are compatible. So there are two graded manifolds. One is called target space, because that's where the fields of this AKSZ sigma model take values. And it is equipped with a homological vector field, this Q, which squares to 0. It is, of course, of degree 1 because it's homological, and the compatible symplectic structure, omega, which has degree n-1, where n is a space-time dimension, and it is invariant under the action of a vector field Q. In addition, you can see from this you can derive the following relation, which is known as a master equation in BV formalism. But of course, it's not a genuine BV formalism because the degree of the symplectic structure is n-1. So it's only in dimension 0 where we can talk about toy. We can only consider this as a toy model. It coincides with the BV structure. And also from this data, it follows that there exists a potential Hamiltonian L, which is a Hamiltonian for the Hamiltonian vector field Q, because Q preserves symplectic structure. So there is a Hamiltonian. And of course, you can also equivalently write this as an equation like this, where brackets is a Poisson graded Poisson bracket determined by symplectic structure omega. So these are equivalent, guys. And in addition, we need to specify source space, which is going to be just a shifted tangent bundle over the space-time. So let's assume in all our example, the source space has the following form. So it's a shifted tangent bundle of X. So functions on these graded manifolds are differential forms. There is a canonical Q structure, which is just a de Rham differential here. And in general, we need a volume form, but there is a canonical one on this source space because it is T1x. We know that we can integrate differential forms, so there is a canonical integration of functions on this graded manifold. So we don't need to worry about density. Okay, then what is nice about this AKSZ construction is that out of this typically finite dimensional data, you build a field theory. So all the structures of the field theory are encoded in the finite dimensional geometry. And many people find it as quite an attractive feature in contrast to standard approach to field theory, where you need to work with infinite dimensional manifolds of field configurations, which of course you can still simplify in one way or another, but it's a lot of work. Okay, so we go to the space of supermaps from our source space to our target space. To make things more explicit, suppose that psi a are coordinates on the target space and x theta are coordinates on the source space. So let me remind you that theta is roughly speaking dx. It's like basis differential forms seen as graded degree one anti-commuting variables. And then out of the data which we had, we can cook up an action. So what we can do, we can pull back our potential function L by a supermap, and then we can pull back the presymplectic potential chi. So as usually to write an action, we need not a symplectic structure, but a potential. So we fix we choose chi such that omega is d chi, and this happens on the target. So we pull back our one form chi and evaluate it on the de Rham differential, which is a vector field on the source space. So this is one form. So this is one form on the source space, and this is a vector field in the source space. So source space, we evaluate one on another, and we get a function of a right degree, because we assume that chi has degree n minus 1, dx has degree 1, so we have a function of degree n, which is a top differential form on our space-time x, so we can integrate. And one can check that actually this functional satisfies master equation. This is a matter of straightforward computations, but what is important is that the symplectic structure on the target space induces the symplectic structure on the infinite dimensional space of supermaps. There is a shift of degree because we need to integrate over the fibers of T1x where coordinates have degree 1. So finally, we end up with symplectic structure on the space of fields of degree -1. So that's what it should be in Bataillon-Vilkovisky formalism, or equivalently, you can write down the respective Poisson bracket, which has the opposite degree, which is degree 1. And you can formulate Bataillon-Vilkovisky master equation just like this. Of course, I am sloppy about what happens on the boundary. So of course, in general, on the right-hand side, you have boundary terms. So terms of the form total derivative of something. And this equation guarantees that this SBV, from this SBV, we can extract, so the general structure is like SBV is classical action, which depends only on fields. This you obtain by setting to 0 all variables of non-vanishing degree. And then there is something like this. So you have the first term involves variables of degree -1, which are known as anti-fields, and variables of degree 1 to compensate the negative degree. And then there are coefficients which are in general field dependent, and the meaning of these coefficients is a gauge generator. So they generate transformation delta phi I of our fields, epsilon alpha, where epsilon alpha are parameters of gauge transformations. So the ghosts are associated to gauge parameters by shifting its new coordinates, which can be considered as gauge parameters with degree shifted by 1. So indeed, this nice geometrical setup allows to construct the BV formulation from out of some nice graded geometrical data. And this is quite in contrast, at least at the time long ago when it was when BV formalism was developed and people started to use it. It was quite in contrast to what typically happened, because typically in physics, the use of BV formalism is to quantize the theory. So you start with an action, and then you need to perform a quantization properly. You need to complete it. You need to find these extra terms containing information about gauge symmetries. In principle, there are further terms there, such that the master equation is satisfied. And then you can use this BV action to formulate consistently the path integral for the system. But here, surprisingly, you get immediately in a AKSZ setup, you immediately get the BV action without without going through the classical action and then completing it to BV action, which is also quite a nice feature, which also tells us that probably, and this is the point of view I'm always trying to advocate, that BV is the right language to talk about gauge systems. And you should immediately think of gauge system as a BV in terms of its BV formulation. It's like a nice category. Of course, it has to be specified because there are different versions. And when we talk about gauge systems, that's a natural That's a natural language. So let's dig a bit more into the structure. So when we consider our supermaps, which are fields of our BV formulation, we can explicitly expand them in terms of thetas, because it's just a Grassmann algebra of the thetas. You see, if we pick local coordinates, we expand our fields in theta, and so we can think of these component fields as coordinates on the space of supermaps. And of course, because theta has degree 1, the component field with k indices, which is a k form geometrically, has degree, which is a degree of the respective target space variable minus k, because the k units of the degree are gone because of theta. They are kept by theta. So the field in front should be should have lower Gauss degree. In particular, even if the target space manifold is positively or non-negatively graded, usually we get fields of negative degree on the space of supermaps. And that's how it should be in BV, because we know that in BV, because of symplectic structure, even if we have a fields in degree 0, which means that we describe something meaningful, we necessarily have fields of degree -1 at least, but usually also -2, etc. And of course, this AKSZ formulation also nicely captures the classical action, not its BV extension. This is achieved just by replacing supermap with a map, so degree preserving map sigma. Then, of course, the space of maps is not a graded manifold, but a usual manifold. So we only have coordinates of degree 0, and this is precisely the classical action, which is encoded in the BV action. Okay. So what equations of motion look like? Equations of motion have the following structure. I decided not to get into invariant formulation of this and use coordinates. So let me remind you that psi a are coordinates on the target. So all of them become fields. On M, all of them become fields, and equations of motion have the following structure. So it's a curvature of Q multiplied by, so of course here I mean QA of psi of x theta, right? Like here. So this is curvature, right? This is curvature determined by Q. And, or in other words, it's a deviation of discrepancy in psi being a morphism of Q manifolds, so-called Q map. So the equations have the following structure. It is this curvature, which is multiplied by the symplectic structure, omega AB. And because in AKSZ setup, omega is invertible, of course, the first equation implies the second, right? So our solutions are just Q maps from source space to the target space. So in some sense, we are talking about generalized flat connections. And if we study gauge transformations, which are also encoded in the BV action of AKSZ sigma model, you can also write them like this. You'll find that these are natural gauge transformations of a connection. So in principle, at first glance, it looks like AKSZ sigma model could only describe some kind of generalized zero curvature equation together with its natural gauge symmetries. And so it's not a surprise that at least for in the finite dimensional setup, it only describes topological models. Okay, and the typical example, which was in the very original paper of this gentleman's, is the Chern-Simons, where equations of motion is precisely the zero curvature equation for connection with values in the connection on a principal bundle. But of course, here the considerations are local, and we think of them just as a one form with values in the Lie algebra. But how Chern-Simons can be can be constructed in terms of in AKSZ terms. It's very simple. You take a target space to be the Lie algebra with shifted degree. You take Q structure to be Chevalier-Eilenberg differential with trivial coefficients of this algebra, so that it is known that it is just a vector field on this shifted algebra. And as a symplectic structure, you can you can just use the invariant form. You assume that your algebra is reductive, so there is an invariant symmetric form. But because our manifold is fermionic, this symmetric form can be traded into a symplectic form on shifted algebra. And of course, it is a Q invariant, and it has degree 2 because coordinates have degree 1. So the constant form has degree 2. And that's why we can construct an AKSZ sigma model in 3 dimensions. We do it, and we find that we just get a standard Chern-Simons functional plus a BV completion. What is a nice formula? The nice formula is how the field content of BV formulation of Chern-Simons sits inside the supermultiplet. So now I pack all my coordinates on G1 into an algebra valued coordinate C. So you think of C is like some coordinates C alpha, T alpha, where T alpha is a basis in my Lie algebra. So it's very useful to work in terms of there is a question. Moment, can you explain on what the degree of a symplectic structure means? Possibly its meaning for physics. Well, I'm not sure I fully. So there is okay, in our setup here, well, it's a standard setup nowadays. The target space symplectic structure should have degree dimension of space-time -1 in order to produce a correct symplectic structure in n dimensions for a field theory in X. So it's kind of fixed. Of course, there are different symplectic structures of different degree. It's a very interesting issue, and I think we'll better get back to this later, because, for instance, the usual Hamiltonian symplectic structure for this theory can be also obtained by the same construction, but you just perform it in 1 dimension lower. So you get a symplectic structure of degree 0, and in fact, that's a very important feature about these AKSZ models, that you can pull it back to any submanifold, for instance, to the initial data, and produce like AKSZ sigma models of different degrees. For instance, in codimension 1, you produce Hamiltonian formalism. I'll comment on this a bit later. Okay. So the formulas here like this. So we work in terms of coordinate. You can think that it is isometrics or Lie algebra valued coordinate. It's isometrics, or you expand in basis. And then you see that.
I'm sorry. May I just interrupt? There's a question. Can you explain what the degree of a symplectic structure means? Possibly its meaning for physics. You mentioned coordinates are degree 1. Probably degree 1 don't have dynamics equations.
No, but that's exactly what I'm talking. Yeah. Thank you, Alexei.
Okay.
That's precisely what I'm talking about. Coordinates in the target space have degree 1.
Okay.
But what has physical meaning and geometrical is the coordinates on the space of supermaps, because these are our fields. And let's consider precisely in this example, let's consider a generic supermap, so which is written here, right, a bit schematically. So it's because it's a function of x and theta, we can expand it in theta, because in theta we can't have theta fermionic, so we can only have 3 terms in the expansion, right? So theta independent, first order, second order, third order. And what are the degrees? So this C, the first one, C naught, has degree 1, right? Because it doesn't have any theta. But this guy has degree 0. And this is going to be interpreted as components of a Chern-Simons connection. But then you also have fields of degree. These guys come in degree -1, and these guys come in degree -2. And it's not difficult to see that the symplectic structure, because symplectic structure descends to this space of supermaps, and essentially it's an integration over theta. You see that those which together form a top form, they are conjugate. So for instance, C0 is conjugated to this guy, C3, because together they form an integration object in 3 dimension. And this guy is conjugated to this guy. And of course, so C2 is the antifield for A, and C3 is an antifield for C0. So you see all the multiplet of BV fields, antifields, which in this example is very simple, but in other examples, believe me, it's not so simple. So it's highly desirable to pack all this into something very simple. And that's precisely what AKSZ construction does. And indeed, here I have explicitly written written the symplectic structure. If you integrate the target space symplectic structure over your source space, you get precisely this structure, right? A star is C2, just dualized, and C is conjugated to C star is C3, but dualized. So you see the physical fields show up as components of this AKSZ superfield. So even if in the target space we have degree like 1, 2, whatever, somewhere in the space of supermaps we are going to find degree 0 coordinates, which will bring us the some physical or geometrical structures. I hope I answered. Okay, and the next example, which is also very characteristic, and it also shows that not only topological theories can be considered. So let's look at AKSZ sigma model in dimension 1. Then, according to the prescription, the symplectic structure in the target space should have degree 0. So it's a normal Hamiltonian formalism symplectic structure, and the Hamiltonian then for the homological vector field, which is omega here, has degree 1. So it's precisely the setup of so-called Hamiltonian BRST formalism, also known under the name of Batalin, Fratkin, and Wilkowski, these 3 gentlemen. And the standard situation that this M is a kind of direct product of a physical Hamiltonian space, symplectic manifold M0 of degree 0, times cotangent bundle over ghost space, which is, let's say, ghost space. So where coordinates are of degree 1. So for instance, here C alpha, on the fiber you have P alpha, and here you have something PQ. Right, that's the standard setup. So let's take this typical example and build an AKSZ sigma model. In fact, you immediately observe that there is one extra guy which you want to plug in, which is Hamiltonian, right? Because we are talking about Hamiltonian formalism. So also there is a Hamiltonian in H0, which you can plug in, and there is a room for it in this construction. So you write BV action of this generalized AKSZ sigma model, where you have explicitly theta dependent terms. Strictly speaking, it's not AKSZ. You perform integration over theta to get the component action, and you see that this is nothing but BV formulation for the action of a constrained Hamiltonian system, which is determined by constraints which are sitting encoded in terms inside omega, and Hamiltonian, which we had in the beginning, and this is a standard kinetic term. What is interesting that here in the action we have so-called Lagrange multipliers which enforce the constraints, and they somehow show up automatically because they show up precisely as physical degree 0 components, which are one form component of the ghost. So we have a appearance of like a new, exactly same mechanism. So there is a ghost coordinate of degree 1, it's unphysical, but on the space of supermaps, it gives rise to Lagrange multiplier. And this is in fact a very important point, which is known in gauge theories very well, that temporal components of gauge fields are Lagrange multipliers. So there is like a deeper structure here. And another message which we can infer from these considerations, that in fact, if we have an AKSZ sigma model, and if we drop the integration over t and theta, what we get is a Hamiltonian formulation. So this somehow it's not a Lagrangian nor Hamiltonian formalism. It comprises both in a kind of unified manner. Okay, and finally, this also gives a very nice relation between the brackets. You can see that it's of course formula a little bit schematic, but it can be made precise. So the Battalion-Wilkowski bracket of degree -1 is a Poisson bracket, which is integrated over the source space. So that's the relation between target space bracket and space of fields bracket. So it makes explicit the isomorphism, which was of course discussed in the context of gauge theories before. So you can give a meaning. So in fact, this map precisely it can be made explicitly into isomorphism, which sense, of course, it has to be restricted to right objects, and it gives an isomorphism of certain algebras, including, for instance, global symmetries, etc., between Hamiltonian and Lagrangian formalism. Okay, so what we learned by studying these toy old models. So in fact, that AKSZ construction can be extended to capture the non-diffeomorphism invariant systems, and this happens by bringing by allowing the structures to depend explicitly on the source space coordinates. So you need to go from a target space to a bundle. As I already mentioned, this unifies in a certain sense Hamiltonian and Lagrangian formalism, and this explains why it found many applications in studying theories on manifolds with boundaries. And in fact, it can be also used to study not necessarily boundaries, but any submanifolds, because it gives in a certain some charges associated to submanifolds. So it's a very flexible framework. So what we want to extend this framework to the setup, to the case where we are interested in not necessarily topological theories. So at best, it would be to extend this formalism to generic gauge, local gauge theories. I'm only interested in local for some reasons, because otherwise it becomes infinite, everything. And to see what's going on, let me remind you that when we looked at equations of motion, we saw that it's a kind of generalized zero curvature equation, so it doesn't leave us many chances to describe degrees of freedom. Of course, this construction can be generalized to non-topological theories, and it was done. But the price for this is to allow infinite dimensional target. Roughly speaking, you need to consider something like jet bundle of a BV formulation for local gauge theory and put it to the target. Then you will find an AKSZ representation for the theory, at least at the level of equations of motion. The issue of Lagrangian is a little bit subtle. This you can also do, but this requires additional work. It's not so straightforward. However, there is an interesting alternative to this, and it becomes obvious if we look again at these equations of motion. I forgot here, of course, it is equal 0. These are our equations of motion. It is, again, it's a curvature multiplied by this omega AB. So another way to let degrees of freedom enter is to allow for degenerate omega. Then we don't get full curvature, but we only get part of the curvature. And this is precisely what we need, because, for instance, Einstein equations, you can think of them in Cartan formalism as a condition that the full curvature, of course, it vanishes in the sector of torsion, but the trace-free part of the curvature is unconstrained. The trace is killed, which is Ricci tensor. So you say Ricci is 0. It's Einstein equation. This is precisely killing the part of the curvature. So the guess is that this is what we could utilize, and this is precisely what happens. Let's have a look at gravity. It's not for nothing I gave this example of gravity. And we start precisely as if it were Chern-Simons, but now let's suppose we are in 4 dimensions. So we take Poincare algebra G shifted by 1. Here it is. Q is again just a Chevalier-Lindbergh differential. Here I pick, so Xi corresponds to translations of Poincare algebra, and Rho corresponds to Lorentz rotation. It's orthogonal, pseudo-orthogonal affine algebra, so you have translations and you have generalized translation, generalized rotations, Lorentz rotations. So this is just a structure of the algebra. You read off this from commutational relations, and then you observe that on this algebra, now we are in 4 dimension. So even if it were semi-simple and we had a invariant form, it wouldn't help because the form has wrong degree. Now we need a symplectic structure of degree 3, and in fact there is an invariant one. A very nice one, this, which we cook with the help of a total antisymmetric tensor, which is a Lorentz invariant, and it's easy to check that it is invariant with respect to this Q. But what is interesting, and this is a very important point why it works, that this symplectic structure is not regular, strictly speaking, because it is proportional to this Xi, so it vanishes at Xi equals 0. So here is a typo. Okay, so because you have a Hamiltonian vector field, you have a Hamiltonian L. Everything is like in AKSZ setup. You can repeat the construction, write down the action, and what you find Cartan-Weil action. So it's a formulation of Einstein theory in terms of frame field. So E is frame field, and gamma is spin connection. So these are 2 components of the Cartan connection, which describe this geometry. So sometimes it's referred as Cartan formulation of gravity. Okay, and with this idea illustrated on this example, we can try to find a general setup. It's a bit of a try and error story, but finally there are some nice axioms. It took some time to figure out what are nice ones and very general ones. I don't pretend this is the best formulation. Perhaps it can be done slightly differently, but not perhaps too differently. So what we need is to formulate the general situation. We need a notion of pre-Q bundle. So what does it mean? It means that it's a bundle, it's a fiber bundle such that the total space and the source space are equipped with equipped with vector fields of degree 1. Again, everything is Z-graded, but now, so it's precisely like a Q bundle, but now we don't require this. We don't require this. It can be non-zero. It can be 0 or it can be non-zero. We don't require the nilpotency, so it's not a homological vector field. And in fact, maybe it's a good point that maybe I could, does it work like, no, it doesn't work like this. Maybe I could explain the idea, because it's very simple beyond the idea behind this generalization. Let me, I hope you, sorry, let me do something. Oops. Okay, so here I can write. So the idea is very simple. Suppose we have a manifold, which is presymplectic, M, omega, and we have a vector field, Q. And suppose the degree which I call ghost of Q is 1, and d omega is 0. It's a 2 form. So it's a presymplectic manifold together with a compatible vector field, compatible in this sense that if we take a Lie derivative of omega, we get 0. And we impose additional condition, IQ, because it's odd, we can substitute it 2 times we can substitute it twice into the 2 form, and suppose that this is 0. And then, so suppose we are given with this, then there is a very simple statement that if we identify subalgebra of functions which consist in functions on M, such that kf is 0 for any k from the kernel symplectic structure, then q squared f equals 0 for all f in A. So if we consider subalgebra of functions annihilated by the kernel distribution of omega, so once we have a presymplectic structure, we have an involutive distribution of its 0 vector fields. And if we now consider functions invariant with respect to this distribution, then Q is nilpotent on this subalgebra. Of course, if omega is regular, it just means that Q on symplectic quotient, if we have a regular presymplectic structure, at least locally, we can take a quotient because we have an integrable distribution. So we go to the space of leaves. We assume that locally it is a fibration. We assume that it is a fibration. And functions there precisely functions invariant with respect to distribution. And there Q is nilpotent. Q on symplectic quotient. So that's actually the idea. Of course, there are few intricacies which I have to explain, but the idea is very simple. So if there is a nice way to encode Q manifolds where Q is homological, symplectic Q manifolds, that's precisely what we need in AKSZ and in BV, in terms of presymplectic Q manifolds, where the condition of nilpotency is weakened to this kind of generalized master equation. And then you recover the symplectic Q manifold by passing to the symplectic quotient. This is the idea. Of course, it's not so simple technically in the setup which we need in field theory, because it's not just a manifold, it's a fiber bundle with additional structures and everything should be compatible, so it requires some work. So here are the axioms. They look slightly different. For instance, instead of, you would expect here equals 0, but in fact you have this, where L is a Hamiltonian for Q. In fact, it's not so important. Usually you can get rid of this term, but the invariant formulation is achieved in these terms. So you require immediately compatibility between presymplectic structure, Q field, and the potential, the Hamiltonian for Q field. And here you see that this is not 0. There is a new guy entering the game. And this I is the ideal in the algebra of differential forms on the total space, which is generated by non-vanishing forms of non-vanishing degree pulled back from the source. So in coordinates, in standard coordinates, which I always use, this x, mu, theta, mu, this ideal is just generated by these guys. So it's a very simple thing. But this is important if you want explicit dependence on space-time of your objects. Okay, and let's see how it works. So we have a definition of this weak presymplectic. For some reason, there is a strange name. So the first example is scalar field. So what is our finite dimensional manifold? I don't pay any attention. Everything is local and globally trivial to avoid all these words. So I have essentially my fiber has two coordinates, phi and phi a. A is a space-time numerates. It's an index of space-time coordinates. These are coordinates of degree 0, and of course I have my space-time x and theta, and Q is like this. Q field is like this, and the presymplectic structure has the following form. Here is the potential. It can be thought of as a codimension 1 horizontal form because thetas are dx's, and of course you easily recognize the presymplectic current of the scalar field. So it looks the same. In fact, in general, because it's a non-linear series, there is a potential here. Q is not important, but still everything works. You substitute and you get an action which is a well-known first-order action for the scalar field. Then you can play the same game for Young-Mills. In this case, you take your fiber to have coordinates C, just like in Chern-Simons. C takes values in gauge algebra, in certain reductive Lie algebra, and also introduce antisymmetric tensor of degree 0, just coordinates like this. And the Q structure reads like this. Again, if it is non-abelian, Q doesn't square to 0, so it's not a Q manifold. There is a presymplectic structure, which is Q invariant, and it looks like this. Essentially, F and C behaves like coordinate and momenta for this presymplectic structure. And again, it is not regular. You see, there is thetas to certain power. So it's not a regular presymplectic structure, but still, if you plug everything in, compute, you get a standard first-order action for the Young-Mills. So what we see, the procedure is almost as good as AKSZ. It applies to generic, not necessarily diffeomorphism, not necessarily topological theories. In fact, you can cook up many examples. It's quite simple, so the axioms are sufficiently general in this sense. So what is nice is that we managed to encode a local gauge theory in terms of a finite dimensional geometrical object, which is this pre-Q bundle equipped with presymplectic structure and this Q field. And in fact, these graded manifolds, which I just shown, they are in a certain sense invariant, because in fact it's not a mathematically rigorous statement, of course, but if you study the situation, you will see that they arise as certain truncations of minimal models of the associated Q manifolds, or perturbatively, you can think just of L infinity algebras, which are unique up to isomorphism. So it means that if you study, you will end up with something like that. Again, it's not a mathematically rigorous statement, but it's not too far. Under some conditions, it can be made. Some additional technical conditions, it can be made precise. So we identified some kind of geometrical object which underlies local gauge systems and which knows nearly everything about them. But you can ask me at this stage, what should we do about BV? Because the beauty of AKSZ was not that we could just reproduce in a nice form the action functional of a topological theory, but that together with it, at no price, at no extra price, we get a we get a full-scale BV formulation, which knows everything, which is a good starting point for quantization or analysis of symmetries, counter terms, whatever. It's just a good language to talk about gauge theories. But for the moment, we saw nothing about BV. We don't know where anti-fields sit, right? In fact, you could get BV. So what you need to do, there is a certain technical step I need to spend 2 minutes. So the idea is it's when you work with AKSZ, it is important to identify the additional useful fiber bundle. So what we are dealing with is a bundle over T1x, which is the bundle itself. So what you could do, you could cook up a new bundle, which is going to be a bundle over X, and I call it E bar. And the fiber of this bundle is a space of supermaps. If we want a fiber over a particular point X, so we take this fiber to be a space of supermaps from the fiber of our source fiber bundle, right? Fiber at X, which is just T1X at point X, to the fiber of the initial bundle. And in particular, supersections of this new bundle E bar over X are the same as supersections of our initial bundle. So it's just another way to look at this situation. But already this E bar so fiber coordinates there are roughly speaking these AKSZ fields. And in fact, the presymplectic structure on the total space determines the presymplectic structure on these fibers just by integrating over the fiber, but the fiber is pure fermionic, so integration is perfect. And you get a new presymplectic structure. In fact, I don't have time to get into geometrical details because globally, it's not a presymplectic structure, it's like density valued presymplectic structure, strictly speaking, but it doesn't matter for what we need. What happens is that in interesting cases, this induced presymplectic structure on this new bundle is regular. And this is a condition of quasi-regularity, which is crucial. So somehow when we do this AKSZ-like things with presymplectic structures, which are nice and concise, but we encounter presymplectic structures which are not regular, but they are quasi-regular in the sense that their prolongation to this new bundle E bar is regular. Of course, the proper geometrical words to say here is a vertical jet bundle, because you could consider jets along fibers of T1X, and this is precisely E bar. Okay, with some details. And then this can be made really globally defined. Okay, and now we are ready to formulate the main statement, which is like this. So if we have a weak presymplectic gauge PDE, this is the object I just defined, and such that the presymplectic structure is quasi-regular, then at least locally, this BV-like action, the AKSZ-like action, just same formula, defines a genuine local BV system, so local gauge theory in a BV formulation, and the underlying fiber bundle is the symplectic quotient of this bundle E bar. So you need to get rid of the zero directions of this symplectic form, but not on the initial bundle, but on these vertical jets, on this auxiliary E bar bundle, where it becomes regular. And the physical explanation, of course, is quite clear. So if we just write this BV action, it's easy to check that if a certain field belongs to the kernel of certain direction, belongs to the kernel of our presymplectic structure, shifts in these directions are gauge transformations, and they are algebraic gauge transformations. They bring nothing interesting, and you need to gauge fix. Gauge fix these gauge transformations means passing to the symplectic quotient. And in fact, if you want to, for instance, write down formal path integral, you don't really need to perform this this symplectic quotient explicitly. It's just enough to add additional gauge conditions which get rid of these directions. Okay, and here are examples. We already considered these examples, but now I'll show you how the full-scale BV shows up. Remember scalar field. There are two fiber coordinates which give rise to fields now, but now they're superfields, right? And this, so you get 0 component and you get 1 component, the rest is not interesting. And then you use this presymplectic structure, you integrate over thetas. This is precisely, you induce the presymplectic structure on the space of supermaps, and you get a canonical BV symplectic structure. It's obvious it is regular, so everything was good from the very beginning. So among all the component fields of this phi and phi a, it's only this phi naught and the trace of phi 1 a and these guys, they are not in the kernel. All the rest is gone, and we get a finite dimensional usual BV formulation of a scalar field. But of course, in first order formalism, that's why we have two independent fields, our phi and our phi a, which is like multi-momenta, if you want. In fact, there is, clearly I don't have time to talk about this. There is a deep relation to what's called multisymplectic geometry and multisymplectic formalism in field theory. But of course, what we are dealing now is a BV extension of it. Same happens for Young-Mills. Remember, there are two coordinates C and F. So you run the same machinery, you find a regular presymplectic structure, and you see that among these component fields of C and F, you find ghost fields, anti-fields, the full spectrum of BV formalism for Young-Mills. The same happens for gravity. It's slightly more tricky because the symplectic structure is field dependent. So you find a very nice formulation of BV in these terms, but the symplectic structure turns out to be not in Darboux form. Nevertheless, there is a statement which is not entirely trivial in this setup. The statement is to show that the statement says that this presymplectic structure is quasi-regular. Okay, I really need to stop. So it's 1 hour, right? The time is over. Almost over.
Almost, yeah, few minutes.
Almost. Okay, so just in few minutes. There is a version which I don't have time to talk about, a non-Lagrangian version of the story, which is quite recent. We did it with my PhD student Dima Rudinsky, which is just essentially forgetting symplectic structure in this game. What is needed is just a distribution, involutive distribution, which integrable even in this case we need, which takes care of the kernel. So of q not squaring to 0. So all we need to require is that the square of q belongs to certain q invariant distribution, and all the machinery can be run again. And for instance, you can cook up some nice non-Lagrangian example, which is again looks almost like Chern-Simons, but there is a non-trivial distribution which gives you a BV formulation for self-dual Young-Mills, which is known to be non-Lagrangian. There is no symplectic structure, but still you can find a distribution which produces for you a proper BV BRST complex for self-dual Young-Mills. Okay, there is a last part, let's say, of my talk for which I clearly don't have time, and this was meant to explain how to arrive at all this. Where does it come from? I clearly don't have time for this, but the idea, nevertheless, is that you need to develop some technique, but the main idea is that you need to start with BV formulation, take a total BRST differential, which is horizontal differential plus usual BRST differential. Think of it as a gauge PDE, some kind of generalized AKSZ sigma model, and then reduce it. and transfer there, and the reduction is kind of homotopy transfer. You eliminate, in physics terms, you eliminate generalized auxiliary fields. And then you have, you take a symplectic structure of BV, which is like a top form, top horizontal form, which is two form in vertical direction. And then you do a descent completion of it. So you uplift it to a cogomology of Q from cogomology of S mod DH, because it is only invariant modulo boundary terms. You uplift it, you sum up all these descent symplectic forms to a total form, and you find this, roughly speaking. And this gives you this presymplectic gauge PDE, but then you transfer it to the minimal version. You eliminate as many as possible auxiliary fields or contractible pairs, or if you prefer L infinity language, you go to a minimal model of the underlying L infinity algebra, and you transfer this symplectic structure there. And you again do AKSZ. Now you are in AKSZ setup, presymplectic AKSZ, but you observe that everything, typically you are dealing with something infinite dimensional, but then the thing is that because omega is local, there are only finite number of coordinates which are not in the kernel. So what you do, you like quotient by a regular kernel. It doesn't affect anything because all your structures do not depend on the kernel. And this quotient by a maximal regular subdistribution in the kernel of omega gives you this finite dimensional model. That's how it works, and in some sense it can be considered as a derivation of AKSZ construction. So suppose you don't know what AKSZ is, which is of course kind of sick considerations, but still morally, if you don't know AKSZ, you could have started with, for instance, Chern-Simons and find its AKSZ formulation just by doing these steps, just by building the jet bundle BV formulation, taking total BRST complex, so summing up horizontal piece and the vertical piece, and taking total degree, which treats differential forms and goes on the equal footing, and then taking a minimal model. In the minimal model, you will find that this is just your shifted Lie algebra only ghost state, and you recover AKSZ. But in more sophisticated situations, of course, you recover something else, which is this presymplectic AKSZ. But the story is that, in fact, quite often it's much easier to get the answer than to derive it, because the formalism is very concise, usually, and you more or less see which geometrical structures are in the game, so you could actually guess the answer, and that's what you could do for many models. I listed just few of them, but even for something much more sophisticated, it's not difficult to build such a formulations, and such a formulation automatically contains BV, so it is useful for many things in field theory. But nevertheless, I think my main message is that there are finite dimensional, of course, if you're talking about normal local theories, there are finite dimensional supergeometrical objects, which in some sense underlie gauge theories. I know everything about them. Gauge theory is not necessarily topological and in higher dimensions, very general. And the minimal version of such formalism seem to be unique, but again, it's not a very precise mathematical statement. This also can be considered as a first principle derivation of AKSZ construction. It determines a kind of canonical first order formulation, which people knew anyway that these actions are very, very nice. But now we could also say that they are not only nice, they are in a certain precise sense minimal and invariant. And there is, of course, a big link with Cartan geometry, especially if you do if you do gravity-like models, you see Cartan connections showing up automatically. Even if you start, for instance, with metric-like formulation of gravity, and if you run this machinery, you will end up with Cartan formulation. So you will automatically find this Cartan connection because you know ghosts, and these ghosts will give rise to forms, and these are going to be precisely these forms which you need in the connection forms in which you need in the Cartan geometry. There are many more examples. There is also an interesting direction to study coupling to study background fields. This make it more flexible somehow, this sort of construction. It unifies, if you're talking about variational theories, it unifies BV and BFV, and hence it can be very useful. And in fact, there are some applications interesting to the context of theories on manifolds with boundaries and asymptotic symmetries. For instance, you can nicely think of certain constructs from conformal geometry, like Pfefferman-Graham construction. You can phrase it in terms of these gauge PDEs and Cartan-like geometry. And maybe last comment I'll make is that perhaps it can be also considered from different angle. We know that, for instance, in geometry of partial differential equations, if we define partial differential equations a Levin-Agradov in invariant terms as a manifold or bundle with a Cartan distribution, usually this bundle is infinite dimensional. And if someone gives you a bundle with a distribution, you don't know if it's a normal PDE or it's something sick. So because if you start to study what does it actually describe, you will find like infinite amount of fields which corresponds to equations of infinite order, and you don't know what you're talking about. But this simply, for instance, if we restrict ourselves to variational equations, then we know that there must be this kind of symplectic structure which must be local. And if the symplectic structure is local, even if it is defined on the entire equation manifold, we still know that the system is local. And there are some situations in applications in physics, for instance, in this high spin theory, where people look for invariant criteria of how to identify local systems using in terms of their equation manifolds, roughly speaking, very, very roughly. So probably it's also an interesting application, but I have nothing concrete to say about this. So thank you very much, and sorry for taking extra minutes.
Thank you, Maxim, for this nice presentation.
Maxim, actually that's very interesting to me, and then related to the several point of view. Of course, I work also sometime Luca Vitagliano, and I remember that he wanted to make Vinogradov theory into kind of homotopy theory and infinity theory, and it seemed to me that you did it by finding some minimum model of some structure and infinity structure to related to this geometric form of the Geiger.
Yeah, I think this, okay, it's the part I didn't talk explicitly. That's what we also worked with Alexei. It's this concept of gauge PDE is kind of a merge of PDE of Vinogradov with BV. It's like the differential graded uplift of the Vinogradov notion of PDE. But it is very flexible because there is a naive uplift when you say, okay, I have a PDE and I put on it additional distribution, which is responsible for gauge symmetries. This is a more restrictive notion. And this is kind of straightforward. What is not straightforward is that actually there is this gauge PDE concept where the two structures are kind of unified. You see, we have only one Q structure. It contains, roughly speaking, Cartan distribution, and it contains gauge distribution. And they can be arbitrarily mixed. And this and still we are talking about PDE with gauge symmetries. This is additional twist on like straightforward extension. That's if I answer. Okay.
Yeah, so that means
that's
you
what
can
I believe is
recover
what I believe is interesting is that there is a non-trivial even extension of the naive merge of Vinogradov with this DG story.
Yeah, so that means you can recover on kind of Vinogradov cohomological invariance, right?
Yeah. Because PD is just a particular case. Then it is just identical. It's just graded geometrical reformulation of PD geometry.
And then why that is a minimum structure? That means you have L infinity algebra on this operation M1, M2, and the minimum that M1 equals 0, right?
Yeah, Vinogradov formulation is minimal in this sense because in Vinogradov we already go to equation manifold, right? We don't care where it is embedded. We just have an equation manifold and the distribution there. And from the in terms of today's talk, this is a minimal model because there is nothing to contract any longer. We can't minimize it without losing something. So it's already, and if it is perturbative, of course, it's just a minimal model of the underlying L-infinity algebra. But L-infinity algebra only works locally, right, and formally. But globally, we need to speak about these Q manifolds. Or Q
and
bundles.
you also say something about the Cartan geometry. So is there some relation between Cartan geometry and on this L-infinity algebra and minimum model of this L-infinity?
Yes, I think. Yeah. I think so. It's a way to. So you can think of different geometries in terms of these gauge PDEs.
Yeah.
And indeed, if you go to minimal model where you have like minimal, you already like maximally gauge fixed if you want everything what you could gauge fixed without losing geometry, you already gauge fixed and solved all equations. Then usually you end up with a Cartan-like formulation of your system. I don't know if it is how to, okay, it's probably not difficult to make it more precise, but morally it is just a reformulation of Cartan geometry.
So if you can add in your slide after this lecture some more reference, that would be very great.
Well, I'm not sure it is really. I know that some people studied some kind of graded geometry on top of Cartan. This I heard about, but I doubt that it is precisely in this setup.
I see.
And in this setup, so there is this reference about here. Well, maybe the best is, well, there are a few references to my works with collaborators some time ago where this type of structures are manifest, but it was not made really explicit and detailed as a separate publication. So I don't know how to. I hope maybe we will have something more precise in the future. But if you look at simple examples, even on my slides, there is an example of, for instance, I can show you just the minimal model of Riemannian geometry. You see what it looks like. You precisely have like Poincare algebra, and you have these curvatures, and the Q structure is like this. And if you look for Q sections for solutions of this system, these are precisely Cartan structure equations. So Cartan structure equations appear as equations of motion in field theory terminology of this gauge PDE of this object. So in some sense, it encodes Cartan geometry if you want. But what is nice in this approach, you really see that the model of, like, you start with metric formulation. For instance, you start with metric and jets of the metric, and then you go to minimal model, and minimal model is Cartan. So you have a kind of homotopy transfer from metric-like formulation to Cartan-like formulation. But it's more or less obvious if you look at it, but it's different philosophy. So to really make the link very precise so that mathematicians are happy, I think it's quite some work. But
yeah. Okay, so I just want to add one thing more on the organizer
Thank you,
problem.
everybody.
thank you everybody for the attention, and thank you organizers for organization.